A refrigerant is a substance or mixture, usually a fluid, used in a heat pump and refrigeration cycle. In most cycles it undergoes phase transitions from a liquid to a gas and back again. Many working fluids have been used for such purposes. Fluorocarbons, especially chlorofluorocarbons, became commonplace in the 20th century, but they are being phased out because of their ozone depletion effects. Other common refrigerants used in various applications are ammonia, sulfur dioxide, and non-halogenated hydrocarbons such as propane. The ideal refrigerant would have favorable thermodynamic properties, be non-corrosive to mechanical components, and be safe, including free from toxicity and flammability. It would not cause ozone depletion or climate change. Since different fluids have the desired traits in different degree, choice is a matter of trade-off. The desired thermodynamic properties are a boiling point somewhat below the target temperature, a high heat of vaporization, a moderate density in liquid form, a relatively high density in gaseous form, and a high critical temperature. Since boiling point and gas density are affected by pressure, refrigerants may be made more suitable for a particular application by choice of operating pressures. Refrigerant environmental issues. The inert nature of many hollands, chlorofluorocarbons and hydrochlorofluorocarbons, with the benefits of them being non-flammable and non-toxic, made them good choices as refrigerants, but their stability in the atmosphere and their corresponding global warming potential and ozone depletion potential raised concerns about their usage. In order from the highest to the lowest potential of ozone depletion of bromochlorofluorocarbon, CFC then HCFC. Though HFC and PFC are non-ozone depleting, many have global warming potentials that are thousands of times greater than CO2. Other refrigerants such as propane and ammonia are not inert, and are flammable or toxic if released. New refrigerants were developed in the early 21st century that are safe to humans and to the environment, but their application has been held up by regulatory hurdles due to concerns over toxicity and flammability. History. Early mechanical refrigeration systems employed sulfur dioxide, methyl chloride and ammonia. Being toxic, sulfur dioxide and methyl chloride rapidly disappeared from the market with the introduction of CFCs. Occasionally, one may encounter older machines with methyl formate, chloromethane, or dichloromethane. Chlorofluorocarbons were little used for refrigeration until better synthesis methods, developed in the 1950s, reduced their cost. Their domination of the market was called into question in the 1980s by concerns about depletion of the ozone layer. Following legislative regulations on ozone-depleting chlorofluorocarbons and hydrochlorofluorocarbons, substances used as substitute refrigerants such as perfluorocarbons and hydrofluorocarbons have also come under criticism. They are currently subject to prohibition discussions on account of their harmful effect on the climate. In 1997, FCs and HFCs were included in the Kyoto Protocol to the Framework Convention on Climate Change. In 2006, the EU adopted a regulation on fluorinated greenhouse gases, which makes stipulations regarding the use of FCs and HFCs with the intention of reducing their emissions. The provisions do not affect climate-neutral refrigerants. Uses: refrigerants such as ammonia, carbon dioxide and non-halogenated hydrocarbons preserve the ozone layer and have no or only a low global warming potential. They are used in air conditioning systems for buildings, in sport and leisure facilities, in the chemical pharmaceutical industry, in the automotive industry and above all in the food industry. In these settings their toxicity is less a concern than in home equipment. Emissions from automobile air conditioning are a growing concern because of their impact on climate change. From 2011 on, the European Union will phase out refrigerants with a global warming potential of more than 150 in automotive air conditioning. This will ban potent greenhouse gases such as the refrigerant HFC 134 or Euro, which has a GWP of 1410 Euro to promote safe and energy-efficient refrigerants. One of the most promising alternatives is CO2. Carbon dioxide is non-flammable, non-ozone depleting, has a global warming potential of 1. R744 can be used as a working fluid in climate control systems for cars, residential air conditioning, hot water pumps, commercial refrigeration, and vending machines. R12 is compatible with mineral oil, while R134A is compatible with synthetic oil that contains esters. GM has announced that it will start using hydrofluoroolefin, HFO 1234F, in all of its brands by 2013. Dimethyl ether is also gaining popularity as a refrigerant, but like propane, it is also dangerously flammable. Some refrigerants are seeing rising use as recreational drugs, leading to an extremely dangerous phenomenon known as inhalant abuse. Disposal. Under Section 608 of the EPA Clean Air Act, it is illegal in the United States to knowingly release HFC 134 refrigerants into the atmosphere. When refrigerants are removed, they should be recycled to clean out any contaminants and return them to a usable condition. Refrigerants should never be mixed together outside of facilities licensed to do so for the purpose of producing blends. Some refrigerants must be managed as hazardous waste even if recycled, and special precautions are required for their transport, depending on the legislation of the country's government. Various refrigerant reclamation methods are in use to recover refrigerants for reuse. Refrigerants by class and or number. Refrigerants may be divided into three classes according to their manner of absorption or extraction of heat from the substances to be refrigerated. Class 1, this class includes refrigerants that cool by phase change, using the refrigerant's latent heat. Class 2, these refrigerants cool by temperature change or sensible heat, the quantity of heat being the specific heat capacity x the temperature change. There are calcium chloride brine, sodium chloride brine, alcohol, and similar non-freezing solutions. The purpose of Class 2 refrigerants is to receive a reduction of temperature from Class 1 refrigerants and convey this lower temperature to the area to be air-conditioned. Class 3, this group consists of solutions that contain absorbed vapors of liquefiable agents or refrigerating media. These solutions function by nature of their ability to carry liquefiable vapors, which produce a cooling effect by the absorption of their heat of solution. They can also be classified into many categories. The numbering system was developed by DuPont Corporation and systematically identifies the molecular structure of refrigerants made with a single halogenated hydrocarbon. The meaning of the codes is as follows: subtracting 90 from the concatenated numbers of carbon, hydrogen and fluorine atoms, respectively, gives the assigned R. Remaining bonds not accounted for are occupied by chlorine atoms. A suffix of a lower-case letter A, B, or C indicates increasingly unsymmetrical isomers. As a special case, the R400 series is made up of zeotropic blends and the R500 series is made up of so-called azeotropic blends. The rightmost digit is assigned arbitrarily by ASHRAE, an industry organization. For example, R134 has 2 carbon atoms, 2 hydrogen atoms, and 4 fluorine atoms, an empirical formula of tetrafluoroethane. The A suffix indicates that the isomer is unbalanced by 1 atom, giving 1,1,1,2 tetrafluoroethane. R134 would have a molecular structure of 1,1,2,2 tetrafluoroethane, a compound not especially effective as a refrigerant. The same numbers are used with an A prefix for generic refrigerants, with a propellant prefix for the same chemical used as a propellant for an aerosol spray, and with trade names for the compounds, such as Freon 12. Recently, a practice of using HFC for hydrofluorocarbons, CFC for chlorofluorocarbons, and HCFC for hydrochlorofluorocarbones has arisen, because of the regulatory differences among these groups. Notable blends. Below are some notable blended HFC mixtures. There exist many more. All R400 and R500 hydrofluorocarbons are blends, as noted above. R401A is a HCFC zeotropic blend of R22, R152A, and R124. It is designed as a replacement for R12. R404A is a HFC nearly azeotropic blend of 52WT. R143A, 44WT. R125, and 4WT. Percent R134A. It is designed as a replacement of R22 and R502 CFC. Its boiling point at normal pressure is -46.5 AA degrees Celsius. Its liquid density is 0.485 grams per centimeter 3. R406A is a zeotropic blend of 55 Wt. Percent R22, 4 Wt. Percent R600A, and 41 Wt. Percent R142B. R407A is a HFC zeotropic blend of 20 Wt. Percent R32, 40 Wt. Percent R125, and 40 Wt. Percent R134A. R407C is a zeotropic hydrofluorocarbon blend of R32, R125, and R134A. The R32 serves to provide the heat capacity, R125 decreases flammability, R134A reduces pressure. R408A is a zeotropic HCFC blend of R22, R125, and R143A. It is a substitute for R502. Its boiling point is -44.4 AA degrees Celsius. R409A is a zeotropic HCFC blend of R22, R124, and R142B. Its boiling point is -35.3 AA degrees Celsius. Its critical temperature is 109.4 AA degrees Celsius. R410A is a near-8 zeotropic blend of R32 and R125. The U.S. Environmental Protection Agency recognizes it as an acceptable substitute for R22 in household and light commercial air conditioning systems. It appears to have gained widespread market acceptance under several trade names. R438A, another HFC blended replacement for R22, with 5 components, R32, R125 per Rankine 134A, R600, and R601A, blended in respective ratios 8.5 plus 0.5, minus 1.5%. 45A plus or minus 1.5%. 44.2A plus or minus 1.5%. 1.7 plus 0.1, minus 0.2%. 0.6 plus 0.1, minus 0.2%. The MIN a unregistered trademark Mo unregistered trademark a unregistered trademark. Molecular weight of this mix is 99, resulting in the trade name ASEAN MO99 from manufacturer DuPont. R500 is an azeotropic blend of 73.8 Wt. Percent of 12 and 26.2 Wt. Percent of R152A. R502 is an azeotropic blend of R22 and R115. Air as a refrigerant. Air has been used for residential, automobile, and turbine-powered aircraft air conditioning and/or cooling. The reason why air is not more widely used as a general-purpose refrigerant is the perception that because there is no change of phase, it is too inefficient to be practical. Yet, with suitable compression and expansion technology, air can be a practical refrigerant, free of the possibility of environmental contamination or damage, and almost completely harmless to plants and animals. An explosion could result from refrigerant-type compressor lubricating oils being compressed together with the air. Air is so frequently used as a coolant that air cooling is seldom mentioned in this context. Due to the low boiling point of its constituents, air is less often used as a refrigerant. Water as a refrigerant. Water, non-toxic, low-cost, and widely available, is widely used in water cooling, and if evaporated in the process may be called a refrigerant. Water also commonly serves as a heat transfer and storage material, and in large systems it may actually fill all of these roles. The simplest and lowest cost open cycle cooling systems, known as swamp coolers in the southwest United States, do not even need power for a compressor, merely a blower fan. Humidified air is simply vented to the living space. Portable freestanding units can be obtained at discount stores for less than $200. However, drawbacks of these systems, if improperly implemented, are multiple and severe. The total cooling power of the unit is limited by the fact that neither coolant nor air can be recirculated. If the cooling unit does not have a supply of fresh dry air and the waste air is not effectively vented, Stagnant humid air will make the space more uncomfortable than if it were merely ventilated. An additional limitation of such systems would be that if the air outside is already humid, cooling power is severely limited. This is why such units are not found in areas of frequent and high humidity, such as the southeast United States. If the temperature outside is severely hot, such as over 110 degrees Fahrenheit or 43 degrees Celsius, the simple unit will not cool the air sufficiently for comfort even if the dew point outside is very low. In these instances, more complex systems such as two-stage, indirect direct or hybrid will be needed. While all the drawbacks can be addressed in various ways, the complexity and initial cost of these systems increases to the point that the installation cost comes into competition with Freon-based direct cooling systems. At this price point, direct cooling systems are often chosen even though the long-term energy cost of evaporative systems may be lower. See also, Brine, Uramen, Initiative for Natural Refrigerants, Industrial Gas, List of Refrigerants, Refrigerant Reclamation, References. External links, U.S. Environmental Protection Agency page on the GWPs of various substances.